Hello everyone. In the previous session we have discussed about three-phase circuits. We have started with three-phase circuits, and in three-phase circuits you have learnt about the necessity of three-phase system and advantages of three-phase system over single phase, then generation of three-phase power or generation of three-phase EMF. Okay, so that is using three windings. So in the next topic, so we shall discuss the relationship between the line and phase values of balanced star and delta connections. Because in the last class itself, in the last session itself, I have introduced the circuit called star and delta. So how exactly the star connection looks like and the delta connection looks like. So in this session, so we are going to see about the relationship between the line and phase. Line and, remember, so these two are the very important terms here. So relationship between line and phase values of balanced. Already I have discussed, already I have told you in the previous session that, so what is this balanced circuit or the balanced load? So balanced star and delta connection. Okay, and here, so in a three-phase system or in a circuit, so we have two sets of voltages and two sets of currents. So we have two sets of voltages and two sets of currents. So two sets of voltages are, so one is line voltage and another one is phase voltage. Okay, so there are two sets of voltages, so one is line voltage and another one is phase voltage, and line voltage can be represented as V suffix L and phase voltage can be represented as VPH. Okay, phase voltage can be represented as V, that is the voltage, and suffix PH. PH indicates the phase. So similarly we have two sets of currents. One is line current and another current is phase current. Okay, and here we represent line current as IL, I suffix L, then phase current as IPH. So throughout this chapter, so we are going to deal with these four terms. These four terms, one is line voltage, that is VL, phase voltage VPH, line current IL, phase current IPH. So remember, throughout this chapter we are going to discuss about these four terms. Okay, we are going to find the relationship between this line and phase values both in star connection and in delta connection. So now let's see the relationship between the line values and the phase values in star connection. Okay, so you know how to write the star connection because this I have already introduced in the previous session. So now it should look like this Y. Okay, so look at this. So now the connections are made in this form, in star connection, and we call this as ZPH, or we also call it as this as load impedance, or ZPH1. So we can have either Z1 and similarly Z2 and Z3. However, okay, so we have got three loads here or three impedances, and so these three load connections are given to this three-phase supply. You can just observe. So this point is given to this R. Okay. Since we have three-phase supply, so we have three lines. One is R, Y and B. So remember, so since we have three-phase supply, so these lines are named as R, Y and then B. Okay, the same RYB we have discussed in the generation of three-phase power. Okay, so RYB, and these three lines are given to this RYB, and which is from the three-phase supply. Look at this circuit carefully, and the current which is coming from this point, we call it as IR. Right, the current which is coming from this line, so we name it as IR, and similarly the current which is coming from Y is IY, and similarly we have IB. So here the currents which are considering from the line we call it as line current. Okay, I'll just repeat. The currents which are considering from the line is nothing but line current. And so similarly, what is line voltage? Line voltage means when we measure the voltage across two lines. So when we measure voltage across two lines, that means if we measure voltage from this point to this point, that is from R to Y, we call it as line voltage. Okay, so anything which is related to line, either the current or the voltage, we call it as line values. So remember, the current which is coming or the current which is considered from the line is nothing but line current. So here the line currents are IR, IY and IB. Okay, so there are three line currents. And similarly, so line voltages. Okay, so the voltage is measured across two lines. Across two lines is nothing but line voltage. That means voltage from R to Y, we just name it as VRY. So these are the line voltages. Okay, so how many line voltages we can have? We can have three line voltages. One is from R to Y, and similarly from Y to B, and another voltage from B to R. Okay, so we have three line voltages, that is from R to Y, because there are here two lines. So when we measure voltage across two lines, then we call it as line voltage. So VRY. Then so another one is, look at this, so VRY, and if we measure the same voltage from Y to B, so it is VYB, and another one is VBR. Right? So here we have got three line voltages. So we have three line currents and three line voltages. Now we are clear with the line values. Similarly, what is this phase values? So remember, when we measure the voltage, across the load, then we call it as phase voltage. So phase voltage, when we measure the voltage across this load, across the impedance. See, look at this. So we named it as ZPH. Okay, ZPH, and which is named as Z1, Z2, Z3. Okay, so you can consider in any form. So if we measure voltage across this load or impedance, we call it as phase voltage. So what is a phase voltage now? And of course this point is the common point, and we name it as the neutral point. Okay, so which is given to the ground point, neutral point. And if we measure the voltage from this line, that is from R to the neutral point. See, look at this, because we are measuring the voltage across this load, across the impedance, then we call it as VRN. Okay, why it is VRN? Because we have measured voltage from R, that is line R, to this N. Okay, VRN. So now the phase voltage becomes VRN. So how many phase voltages you can find here? Again three phase voltages. One is from R to N, and another one from this Y to N. Then here, so this is actually B, right? Because this point is B, and B to N. See, here you are measuring the voltage across the impedance or across the load. So here we have VRN, VYN and VBN. Right? So there are three phase voltages. So voltage is measured across the load, that is one point from the line and another point is neutral. Okay, and similarly we have phase current. So phase current means the current which enters through this load is nothing but phase current. Okay, current which enters through this load is nothing but the phase current. But so remember here, since the line current, because here the two impedances are connected in series, since these two phases are connected in series, the line current, so remember in star connection, line current is equal to phase current. So both are same, because the current which is entering, the current which is coming out of this line is same as the current which enters through the phase, okay, through the load. So since the two phases are connected in series, so we can have IL is equal to, or the line current is equal to IPH, the phase current. Okay, so what is this IPH again? IPH means the current which enters through this load, that is from R to N again. So that is IRN, then IYN and IBN, right? So as I have already told you, so IL, the line current, is same as the phase current, since these two phases are connected in series, right? So we can have this relationship directly in star connection, right? So now we have found the relationship, okay, between the line current and the phase current, in star connection. So what is the relationship between the line current and phase current? So both are same. Okay, now we shall see what is the relationship between the line voltage and the phase voltage in the same circuit. So what is the relationship between the line voltage and the phase voltage in the same circuit? Okay, let's see the circuit now. And as I have already told you, so the voltage which is measured between two lines is nothing but the line voltage, right? And the voltage is measured across the phase. Across the phase is nothing but the phase voltage. So here both are not same. Okay, both are not same. Then what is the relationship? So I can write this as VRY is equal to. Okay, now I am trying to express this line voltage in terms of phase voltage. So what is the relation? Now I can write VRY, that is from R to Y. Okay, I have just taken this R to Y as an example, but similarly you can consider even from Y to B and B to R. Okay, for understanding purpose I have just taken from R to Y. So VRY is nothing but VRN plus, okay, so VRN plus again this N to B, isn't it? See, look at this. So I have taken voltage from this R to Y, and this can be written as, because this is equal to, this voltage is equal to the summation of this voltage and this voltage. Okay, so don't you think this voltage, the line voltage VRY, is equal to the summation of this voltage plus this voltage, right? So we can have the equation as VRY is equal to VRN plus that is from another voltage from N to B, because this is Y. This is Y, that is from N to Y. So plus VNY. Okay, so look at the equation carefully. So I have just expressed the line voltage VRY in terms of the phase voltages, so which is equal to the summation of this VRN plus this VNY. Okay, VNY. Now, so in the next step I can have the equation as, so to have the uniformity in the equation, I am taking VRN, so minus, so here I have taken NY, and instead of that, so I will change the polarity, even this can be expressed as VYN. So finally we have VRY is equal to VRN minus VYN. Look at this, here we had this NY, so just to have the uniformity in the equation, so I have taken the negative, just interchanged this Y to N. So finally we get VRY is equal to VRN minus VYN. This is one expression, and similarly we can have two more expressions, so that is from Y to B. So VYB. So what is VYB? Which is equal to, straight away I can write VYN minus VBN. Okay, because RY. So to remember, you can have this RN and YN. Similarly, YB means YN minus BN minus VBN. And we can have one more expression, that is from VBR. So what is VBR? This can be written as VBN minus VRN. Okay, so we can have three sets of equations. But to analyze, okay, to analyze, because still we have not found the relationship, exact relationship between the line voltage and the phase voltage. We have just expressed in terms of the circuit, okay, that is from the circuit. So to analyze this equation, so we need to have the phasor diagram. So we need to express this equation in terms of phasor diagram. So then we can find out the relationship between the line voltage and the phase voltage in star connection. So now we have got these three equations, but to analyze the relationship we can have only one equation out of these three expressions. So now I am taking the first equation. So I am trying to write the phasor diagram, okay, using first equation. And so to start with, always we need to have these vectors, okay, in terms of the phase values. So what are the phase values here, or what are the phase voltages? Phase voltages are VRN, VYN and VBN. Okay, so we have VRN, VYN and VBN. So to start with, so we need to have three lines here. So three lines, right? So three vectors, and one can be expressed as VRN. So initially to start with we can have, okay, VRN, that is the phase value, and remember always we need to start with the phase values here. So one is VRN and another one is VBN and next is VYN. Okay, even the order can be changed here. Okay, so VRN, VBN. So since we have taken in the form of initially R, B and then Y, so we have taken VRN, VBN and VYN. Okay, and once you write the phasor diagram in these three phase values or the phase voltages, so we need to express this equation in terms of phasor diagram. Now, so we have VRN in the equation. So remember, I am considering the first equation. I am considering only the first equation. So we know where is VRN. Okay, now we have VRN. Then, so what is the next term? So we have VYN. So we have VYN. So here we have VYN. But so look at the equation. So we have minus over there. So we have minus. So since actually this is actually plus, but since we have minus VYN, so we need to project this VYN in opposite direction. Now I can write this as minus VYN, right? So I can write this one as minus VYN, because so since we have positive over here, but in the equation you can see minus VYN, we need to project this in opposite direction to this VYN, and I can name it as minus VYN. Okay, now we have obtained this VRN and minus VYN. So one is VRN and another one is minus VYN. And which is the resultant one? Which is the resultant equation? Resultant one is VRY. Okay, so after summing up these two, so we get left hand side we get VRY. So where should I write the resultant one? That is, so between these two, that means VRN and minus VYN. Of course, since this line, the resultant one is the double of these two, so I can write this equation as VRY. So now we can have a parallelogram. So now we get the resultant one, right? And so now I just name it this as O. And of course this is 90 degree. And what is the angle from this point, that is from the line voltage to the phase voltage? Look at this. So already we know that the angle difference between these three phases, is 120 degree. Okay, that is from VRN to VBN it is 120 degree, VBN to VYN 120 degree, VYN to VRN 120 degree. So the angle difference between VRN and VBN is 120 degree. Now, so what is the angle difference between VRN and VYN? Which is 60 degree, because it is exactly half of that. So the angle difference between VRN and VYN Vyn is 60 degree. Then what is the angle difference between this Vrn and Vry? Of course it is 30 degree because it is exactly half of this angle. Okay, so we get 30 degree. So here we get parallelogram, and I'll just name this point as C and this point as A. Okay, just for understanding. So you can name it whatever you want. Okay, so we have O here, C and then A. Right. So now consider the triangle, because our final aim is to find the relationship between the line voltage and the phase voltage. Okay, so now we have understood that the angle difference between the line voltage and the phase voltage is 30 degree. So now consider the triangle AOC. Let us consider a triangle AOC, that means AOC. Right, and so we know that it is 30 degree, and we are expressing this in terms of cos 30 degree. So we have expressed cos 30 as OC by OA. So why it is OC by OA? Because adjacent by hypotenuse. So this is again adjacent OC divided by OA. So hypotenuse. Then so what is OC? So how can we express in terms of the line voltage? So which is equal to OC is equal to Vry divided by 2, because we get this OC is nothing but half of this line. Okay, so don't you think this OC is nothing but half of this line? So we can have OC as Vry divided by 2. Okay, and what is OA? OA. So OA is nothing but Vrn. So now we need to simplify this equation. And before I simplify this equation, so I'll just repeat how we have again obtained. I'll just repeat this. See, initially we had taken the phase values, phase voltages, that means Vrn, Vbn and Vyn. So remember, always initially to start with we need to express in terms of, okay, we need to draw the phasor diagram with respect to the phase values, phase voltages. So we have Vrn, Vbn and Vyn, and so once we get this value, that means Vrn, so we need to satisfy this equation in terms of phasor diagram. So that means minus, so this part is there, so Vrn is there, and where is Vyn? So to obtain this Vyn, so we need to project, because since we have minus, we need to project this in opposite direction. So now we have obtained Vrn and Vyn, and the resultant value is Vry, that is line voltage, that can be drawn in this fashion. Okay, because this is the resultant one. Of course, this is the double of these two voltages. Since this voltage is a summation of these two, so we need to have the line in this form. And once we get, so we need to join this. These points and to obtain the parallelogram. And so here, so you can join this point, that is Vrn, to this point, because here we need to analyze in terms of this cos. And we have obtained the angle difference between this Vry and Vrn as 30 degree. But to express in terms of this cos 30, okay, so we need to have this triangle. So consider this angle as, consider the triangle AOC. So AOC, right? And what is cos 30? Cos 30 is adjacent by hypotenuse. Adjacent means that is OC, and OA is hypotenuse. So what is OC? Which is half of this line, that means Vry divided by 2, and OA is nothing but Vrn. So further we need to simplify this equation. So here, so what is cos 30? Okay, I'll once again write this equation. Cos 30 is equal to Vry divided by 2. Okay, so Vrn. And I can write this as Vrn cos 30 is equal to Vry divided by 2. Okay. So Vrn, and what is cos 30? Cos 30 is equal to root 3 divided by 2, and this is Vry divided by 2. So 2 gets cancelled. So finally we can have equation as Vry, I am writing this, Vry is equal to root 3 Vrn. Okay, so what is VRY? VRY is nothing but the line voltage. Remember, VRY is nothing but line voltage. The voltage is measured between two lines. So straight away I can write this as line voltage VL, and which is equal to, so root 3 into, and what is VRN? VRN is the phase voltage VPH. Okay. So finally we have found the relationship between the line voltage and the phase voltage in star connection, which is VL is equal to root 3 VPH. Now let us see the same relationship, that means the relationship between the line values and the phase values, both in terms of the current and the voltages in delta connection. So now let's see the relationship between the line values and phase values in delta connection. So now look at the circuit carefully. So we have, in terms of these impedances are arranged in the form of delta. Okay, and so look at this, it is arranged in the form of delta like this, and so these are the impedances, and so we can call it as Z1, so Z2, Z3. So however, so you can change the you can arrange in any fashion. So Z1, Z2, Z3, and look at this. So here this point is given to R, and this point is given to Y, and another point which is given to B. So these three lines are, that is from the three phase supply. Okay, so which are named as RYB, and look at this. So there are 3 points in the delta connection, and these 3 points are, okay, so connected to these RYB. Now, so let us analyze the circuit, and so let us find what are the line currents and what are the phase currents, so what are the line voltages and phase voltages. Okay, so now the current which is from the line I, that is from the line R, is named as IR. Okay, as I have already discussed in the previous topic. So the current which is considered from this line R is named as IR, and similarly we have IY and so IB. Okay, so there are three currents. Remember, the currents which are considered from the line are called as line currents. So now the line currents are, so IL is equal to line currents are IR, comma IY and IB, right? So these are the line currents. And so what are the line voltages? That means VL. So remember, whenever we measure the voltage across okay, or between two lines means that is from R to Y. So VRY, and then so VYB and VBR. So these are the line voltages, right? These are the line voltages. Then, so what is the phase? Now what are the phase currents here? The current which is passing through these phases is nothing but phase current. Okay, the current which is passing through these phases or the loads or impedances is nothing but phase current. Now, so you can just see the direction. Now the direction is considered, okay, in this form, because it has got only one loop, so I need to have only one direction. So look at the direction. Okay, so it is flowing in a single direction. So now the direction is like this, and so now the current which is passing through this phase or the load is named as IRB, that is from R to B. Look at the direction here. The current which is passing through this Z3 or this particular phase is nothing but IRB. And similarly, so what is the current which is passing through this Z2 or this particular phase, that is from B to Y? So we can name it as IBY. Okay, because it is from B to Y, so IBY, and the current which is passing through this phase is nothing but that is from Y to R, so we can name it as IYR. So now what are the phase current? There are three phase currents. One is IRB, IBY and IYR. So we can have the phase currents as IRB and then IBY, and so we have IYR. So these are the phase currents. And so what is the phase voltage? Phase voltage. So phase voltage is nothing but what? The voltage is measured across the phase. So the voltage is measured across this point, okay, either or across this point or across this point. So don't you think the voltage is measured across this R2Y is same as voltage is measured across this particular phase, right? So I'll just repeat, voltage is measured across these two lines. That means VRY, okay, is same as voltage is measured. Look at this, voltage is measured this point. Okay, so let us call it as VRY. Don't you think this voltage is same as this voltage, right? Since this phase is connected across the same point, across this R2Y. So now, I'll just repeat, now this phase voltage, now we call it as this as phase voltage. So this phase voltage is same as line voltage. So remember, the phase voltage is equal to line voltage in delta connection. So in star connection, IPH is equal to IL, but in delta connection, VPH is equal to VL. So let us analyze or let us find the relationship between the line current and the phase current, okay, in this particular circuit. Okay, so here with respect to the line current and the phase current, so you know which is the line current. So line current means IR. So do you think here the line current is same as the phase current? No. Okay, so because here the phases are connected in parallel, so currents are not same. And so let us have a relationship, let us have an equation of this line current and the phase current using this circuit. Now I can have, so IR, look at the direction, this IR current is entering the junction and IYR current is also entering the junction. Remember, this is the phase current and this is the line current. So both the currents are entering the junction and this current is leaving the junction. So based on this, that is by applying KCL, Kirchhoff's current law, we can have the equation as IR, okay, IR plus IYR. Okay, why it is plus? Because both the currents are entering the junction, and this current is leaving the junction, which is equal to IRB, right? So now we have just analyzed only this part. Similarly, we can analyze the other part, which is IY. Okay, see now these two currents are entering the junction. So IY is entering the junction, IBY is also entering the junction. So IY plus IBY is equal to, so these two currents are entering the junction and IYR current is leaving the junction. So which can be written as IYR. Okay, and similarly we can have one more equation, that is, see look at this here, IRB is also entering, IB is also entering the junction. Look at the direction. So IRB is entering the junction, IB is also entering the junction, but this current is leaving the junction. So with this actually we can have IB plus IRB is equal to this current is leaving the junction. So IBY. So we can have three equations, right? We can have three equations, but let us stick on to only one equation and analyze the circuit and write the, that is to draw the phasor diagram. So consider the first equation, IR and IYR both are entering the junction and IRB is leaving the junction. Now in the next step I can write, because I want to have only the line current in the left hand side. So IR is equal to IRB minus IYR, right? So that means I have just shifted this IYR other side, so I get minus. Similarly, we can also have similar kind of equation, but let us stick on to only one equation, that is to draw the phasor diagram. So let us call this equation as 1. Okay, let us call this equation as 1. So IR is equal to IRB minus IYR. So now based on this equation, I am going to draw a phasor diagram finally to find the relationship, okay, that is the line current and the phase current relationship, okay, in delta connection. with this equation, so we are going to draw a phasor diagram. So phasor diagram, as I have already told you, initially to start with, always we should have the phase value. So what are the phase currents here? Okay, so now based on the circuit that we have discussed in the, that is delta connection. So here this direction was IYR, IRB and IBY. Okay, so initially to start with, to start the phasor diagram, so we need to have the phase current. So which is the phase current? So let us have the first one as IYR, so IYR, and the next one as IRB, and so here this last one as IBY. Okay, so according to the direction of the currents which we have analyzed in the delta circuit, have taken the phase currents here. Okay, IYR, IRB and IBY. Now look at the equation. So we have IRB. Okay, so we have already IRB, but we have minus IYR. So where should I draw minus IYR? Already we have IYR. So remember, this is actually IYR, and so we need to project or we need to have that minus IYR, okay, in opposite direction of this IYR. So we need to project this in opposite direction. So we get minus IYR, right, minus IYR. And once we get this minus IYR, then so what is the resultant one? That is, see, we have IRB and minus IYR, and the resultant one is IR. So where should we draw the resultant one? That is at this point, which is IR. The steps which I am following here, which is similar to the previous concept that we have analyzed in star connection. So initially we need to have this equation, and the next step is we need to have the phase currents here. So IYR, IRB and IBY. Later we need to analyze this equation in terms of phasor diagram. So we have already IRB, and to have that minus IYR, so we need to project this in opposite direction. And so where do we get the resultant one? That is exactly the middle of this middle line is IR. Now so we should have, so we need to join these lines to have the parallelogram. Okay, and here to find the angle over here, so that means 30 degree. To find the angle difference between the line current and the phase current, so we need to have the angle. What is the angle between the line current and the phase current? So you know that the angle difference between these two lines is 120 degree. Of course, that is, even from this point to this point is 120 degree, and from here to here it is 60 degree, and from this point to this point it is 30 degree. So now the same step needs to be followed. So here it is named as O. Okay, so O, and then so this is C and this is A. Okay, whichever the name you can consider. And how do we analyze? So as we have did in the previous one, so cos 30 degree is nothing but what? Cos 30 is nothing but that is OC. Okay, so OC divided by OA. So since we have named this point as OA, so I have taken this, that means adjacent by hypotenuse. So if I consider adjacent, which is OC, and then so hypotenuse as OA, then what is OC here? What is OC? OC is nothing but half of this line. So straight away I can write this as IR divided by 2 and divided by what is OA? OA is nothing but IRB, which is equal to cos 30. Okay. So similar kind of equation we have discussed in the star connection. And what is cos 30? Cos 30 is root 3 divided by 2, and so I'll just multiply this IRB over here. So and what is IRB? IRB is nothing but okay, phase current. Remember, IRB is nothing but phase current. So phase current straight away, so we can write IPH, which is equal to what is IR? IR is nothing but the line current. Okay, so divided by 2. So 2 gets cancelled. So finally we can have the line current IL is equal to root 3 into IPH. Okay, look at the relationship between the line current and phase current. So line current IL is equal to root 3 into IPH. So here in the delta connection, so we have found that VL is equal to VPH, okay, that is in terms of voltage, and in terms of current we have IL is equal to root 3 IPH. This is in delta connection, but in star connection, so we have found that IL is equal to IPH, right? So this is in star, and so VL is equal to root 3 VPH. Okay, I hope you have understood the relationship between the line values. Okay, line values means it could be line current or line voltage, and the phase values. Phase values means phase current and phase voltages both in star connection and delta connection. Thank you.